So we said every surface that's not black will have a surface resistance. Okay, that surface resistance is the 1 minus epsilon I over AI epsilon I. Okay, so depending on his epsilon I and his area, you will get that surface resistance that will basically separate you from your black body radiation. So over here, if this is J and this is I, this is sigma Tj to power 4, this is sigma Ti to power 4, and you will have 1 minus epsilon I over area I epsilon I over here, and over here you have 1 minus epsilon J over area J epsilon J. Okay, then you will have your radiosity, your J. Okay, that's smaller than your EB, J or ABI. Okay, and so this is the easiest problem. This is just two surface heat transfer by radiation. Things get complicated if there are three surface, but you still can do it in the homework. And if it's like four surface, then you cannot do it by yourself. I mean, you need an Excel file or a computer program that do the simulation for you. All right? So why is that? Because so we finished the first part of the lecture by saying that how are you going to get the J? If we want to get the Q, we need the J. But when you remember, what was the J again? It was the addition of two things. Radiosity was two things, right? It was your own, a fraction of your black body radiation, and what you are reflecting from the, and the incident radiation has to do with the other guys. So it kind of, you cannot really get your J by yourself or by just depending on your own temperature. It has depend on the other guys. Meaning the J of you and the J of the other guy need to be solved together. Meaning there are two equations, two unknown. And you solve for the two J's. And if there are three surfaces that are radiating with each other, the three J's will come from solving three equations in three unknown. Okay, and so you can do three equations, three unknown in the homework, but not in the exam probably, right? It will be tough. But you can do it in the homework, and four equation, four unknown, well, that's for the computer to do it, right? You just make a system of four equation, four unknown, and then MATLAB or MathScat or anything can solve four equation, four unknown for you. All right? So that's physically the reason why. Mathematically, let's see what are those equations. So again, what we are interested in, we are interested in the heat transfer by radiation, like what we have been doing all this course. In this course, we try to calculate Q by conduction, by convection, by radiation. That's our job. All right? And so we said that the Q coming here would be this minus this, E minus J over that resistance. Okay, I got the resistance, but I don't know the Q, and I don't know the J. And so that's basically one equation in two unknown. Doesn't work. If I do it from the other side, how much Q is leaving, I will have the same problem. I don't know the Q, I don't know the J. But if I look to the two of them together, okay, I will be able to do it. I'll be able to get the Q and the two J's if I want to. How is that possible? Well, if we look to the two of them together, we have to consider what's the resistance between them. Okay, so this slide is basically trying to tell you, you are done, you managed to get the resistance of each surface, right? Now let's try to find the resistance between the two of them, between surface I and surface J. So here he's calculating the net flux leaving I and going to J. Well, that's two-way direct highway, kind of two-way road, right? There is Q leaving I and going to J, and there is Q leaving J and going to I. And the net difference between them, that would be the net at the end of the day. If again 100 watt going this way and 80 watt coming that way, then at the end of the day there is 20 watt going only in the net. Okay, so that's kind of the net. The net, he's trying to make it in italic, but it doesn't show up here. So the net rate between I and J is the difference between two things. This is, so now he cannot say that you are radiating with EB, the black body. He's basically saying radiating with J, because he realized that, well, you have surface resistance. So that J multiplied by the A, this is all the radiation leaving I. Multiplied by Fij, that's basically a fraction of this guy going toward J. And the same thing here. This is all the radiation leaving J. Again, why it's not simply Aj multiplied by sigma Tj? Because J is not black body. Sigma has epsilon. Sigma has a surface resistance. So what leaves J is, what leaves body or surface J is basically its radiosity. Jj. Okay? This is everything leaving J, and this is a fraction going to I. Alright? And reciprocal rule is that Ai Fij is the same as Aj Fji. So let's pull them out. Pull one of them. Let's pull Ai Fij. Let's pull this guy. Ai Fij. So what you end up with is Ji minus Jj. If you put this, if you take this and put it under here as 1 over this guy, the Q, net Q between I and J become J minus J over a resistance. That resistance is simply 1 over Ai Fij. So if you have J1 and J2, the resistance between them to radiation is simply 1 over area 1 F12. Or you can also call it 1 over area 2 F21. It's the same thing. But that is the resistance between them. And the Q, Q dot 1, 2 net is basically J1 minus J2 over that resistance. Okay? So now one of you should say, well, how is that gonna help me? So you are saying that Q dot Q12 is J1 minus J2 over R12, which is 1 over area 1 F12. Well, yes, I got the resistance from the table geometry, but I don't know those guys. I don't know the J's and the Q. How am I gonna do that? Anyone can help? Huh? No more equation, we are done. Those are all the equations. You can do it. Can anyone give me the Q? Let's solve for the Q. This doesn't work. This equation doesn't work because 3 unknown. What will work? How can I get the Q? 1, 2. Anyone for a free quiz? I can't hear.
It's the same for the whole system.
What do you mean? You're right. What do you mean? Give me Q1, 2. No, that's right. Say it. Say. What do you want to say? E. E sub B. And then you don't get free quiz. You have to finish. So let Tony get it. What do you say? A, B minus. We wrote that before, and we know the problem. It's we don't know the Q, we don't know the J, right? That's what we said here.
Set up equal to the Q's are equal to the whole thing, so you can set those two equations equal to each other. That J minus that equation you have over on the right, you set it equal to the DB minus.
So you are saying make it like this and put the R surface 1 here and let it equal to this. And then how can I get my Q? I still don't see it. No, because I have J1 and J2. You got your free quiz. ABI minus ABJ divided by total resistance. So the 3 resistance are in series. And so the Q is AB1 minus AB or ABI minus ABJ over the 3 resistance RS1 plus R12 plus RS2. And so this is the resistance of the first one, this is the resistance between them, and this is the last resistance. So it's kind of 2 surface resistance and space resistance. So surface resistance and space resistance. And you get your Q from 1 to 2. Right? Very good. So that's for two body. And actually, let's solve some problem before we go to the more complicated problems. So that works, okay? That formula works. But sometimes if the two body are kind of standard, like we see them all the time. We see them all the time. Like for example, two plates like this. You see this? This is basically plate 1, plate 2, T1, T2, epsilon 1, epsilon 2. And because they are infinitely long, F12 is, can you read that? Everything leaving 1 will have to fall in 2. Because first, to start with, F11 is 0. He cannot see himself. Alright? And because they are infinitely long, he doesn't see the ends. Nothing can leave the ends. I mean, if it's just like 1 inch over 1 inch, some stuff can leave, can escape. But if it's infinitely long, F12 is basically 1. So you can follow that formula that you would say, well, Q12 is, and then you would say it's sigma T1 to power 4 minus sigma T2 to power 4, that's EB1 minus EB2, over, and you would say 1 minus epsilon 1, area 1, epsilon 1, plus 1 over area 1 multiplied by F12, which is 1, plus 1 minus epsilon 2 over area 2, epsilon 2. But then if you work the mass, you realize that this is basically simply going to be this. So then people put this in a table. It's in our chapter 13. And so in the exam, if you just have two parallel plates, infinitely long parallel plates, you don't have to actually write the formula and try to come up with your F12. You basically just hit this formula and use it. Right? Same thing for two concentric cylinders. So he's basically talking about one cylinder inside another cylinder. Right? So the smaller cylinder, radiation F1, all will end up hitting 2. So again, F12 is 1. Here, F21 is not 1. Right? Because there is F22. Right? And so this is the formula for two concentric cylinders. And this is the formula for two spheres. Alright? And here is for one surface that's very tiny compared to another surface. And is completely surrounded by that surface. That's basically a surface radiating to the dome, to the sky, to our sky dome. That would be the radiation leaving it. So that homework problem, the aluminum droplet that was trying to cool down, and it was radiating to the air, and it was so small, and all it can see is the air around it. That was the formula that we used. Remember? It was the area of the droplet, area 1. Not the infinity, not area 2, not the sky area. Area 1, sigma epsilon 1 of the aluminum, T1 to power 4 minus T2 to power 4. Remember, T droplet minus T air. That was the formula. Okay? That's also would be the formula of you sitting outside radiating to the outside world. Because they are so small compared to that dome as well. Okay? So those would be the table that we would use. Let's solve a problem on this. Yeah. So this was in an exam 1 year. So two internal diameter double walled spherical tank. Right? So it's not a sphere, it's not a cylinder, it's a sphere. That was the first mistake that students would make. So those are two spheres, right? And inside they have ice. So the ice is basically sitting at 0 degree. And the wall is 0.5 centimeter thick, and there is 1.5 centimeter. It's airspace between the two of them. Well, he said vacuum over here. And it's evacuated in order to minimize heat transfer. So basically, since there is no air to conduct, The only mechanism for the radiation is radiation. There is no convection, there is no conduction, there is no fluid to move the either by conduction or by convection. It's only radiation from the hot to the cold. Right? So the surface surrounding is evacuated, surrounding the evacuated surface are polished so that each surface have emissivity of 0.15. So they make them shiny and polished so that they wouldn't radiate. If they are black, they will radiate. So again, the soot in a fire, when you start the flame and the flame is really kind of black, that soot particle, they emit like crazy. They are the reason why the radiation is very strong in the flame. Okay, so a sooting flame basically radiates very, very strongly. Alright? So in order to minimize that radiation, they basically make epsilon 0.15. And he gave us the temperature of the outside is 20, the outside tank, outside wall, and inside is 0. And he said determine the rate of heat transfer to the ice water in the tank. He would like Q dot, how much Q dot will leak. And because of that Q, then how much ice will melt during a 24-hour. So let me solve second part first. Let's assume we got the Q dot. How do you find out how much mass of ice will melt during 24 hours? For the ice to melt, he needs joules, right? And the joules that he needs for every kilogram of ice to melt, he needs how much joule for each kilogram of ice to melt? You need to give him CB delta T. That's if you have temperature difference and he's moving across that temperature difference. So the joule he need to do this is CB delta T. But if he's changing his phase, if he's going from liquid to vapor or from solid to liquid, then he would need the latent heat, right? The basically the is basically heat of HIV. So if I put my hand on the Q dot, that's how many joule per second. What should I do for it to figure out how much mass of ice melting? Imagine this, we calculated this, and let's call it 107. It is 107 watt. That's how much heat is leaking by radiation from the out to the inner. What should I do with it to calculate the mass of ice that will melt? So I should, to get how many joules during the 24 hour, I should multiply it by
24 times 36.
Excellent. And so this is how many joules will come in. Then what's the relation between the joules coming in and the ice that will melt? This will be equal to here all those joules. I don't know, 1,000 joule. How much ice you will melt with that? This should be equal to what is the equation? I'm just asking for the equation. Here, this is the Q that he will get during 24 hours. You got it right. Let's multiply the rate by the time. Then those joules will be equal to mass multiplied by the latent heat it takes to melt. Right? This is a kilogram, and this is the joule per kilogram that it takes to melt. Correct? This, you open the table for it, and basically it's 337 10 to the power 3 joule per kilogram. So every kilogram of ice to melt, you need to give him 300,000 joule, or 3,000 kilojoule, 300 kilojoule. So what he will take this heat, he will break the ice into water at 0 degree. He didn't change his temperature. He's just turning from solid to liquid. You want to take his up, you give him even more joules. But this is how much joule will take to melt the ice. Okay? And if this was like steam boiling or something, you multiply M by H Fg, right, in the TS diagram. Okay, so that was the second part. So how much is the mass? You will end up with 27 kilogram. So the answer is 27.8 kilogram of ice will melt during a 24-hour period. Now the first part, two spherical tanks radiating to each other. I could go with EB1 minus EB2 over the surface resistance plus the geometry plus the, or I could basically just go here. Where's my table? And say, here is the sphere. Two concentric spheres. I'll take this and then move it to my answer sheet like this, and say my Q12 is area 1 sigma T1 to the power 4 minus T2 to the power 4. So you need to make sure what's epsilon 1 and what's epsilon 2, right? Like which one. So if you are using that formula, you have to go to the table and basically figure, did he call the smaller one, the smaller is 1 or the bigger? So the smaller is 1 and the bigger is 2, right? Right? And so we got the epsilon, it was 0.15, both epsilons 0.15, and the R2 and the R1 are given to us, right? And you work the T1 and T2 was also given to us, and remember it has to be in Kelvin. So when he said it's 20, you better write it as 20 plus 273 and the 0 plus 273, right? And so this what will end up being 107.4 watts. Okay, so all those standard surfaces, we basically just use the formula for them. Now if we are radiating to more than one surface, then our Q leaving our black body to the J, our own J, this is our surface with his own surface resistance. Will end up being split to different surfaces. Some part will go to I, to 1, 2, 3, 4, and each Q would basically be the difference between the J's over the R, J's over the R, J's over the R. Okay, so let's do an example on this. Here. So he said this is a long furnace, so normal to this page, this go forever. Okay, so it's kind of a 2D problem then, because it's infinitely long. And so that long furnace basically is used for stress relieving and annealing. So they put the workpiece there and they heat it, and then after that maybe they quench it or something. And he said the geometry is 3 meter by 3 meter. That's the square over here. Okay, the roof is at 1400, and the wall is 1700, and the floor is 600. Okay, maybe because they have electric heaters or something in them, that's why they get hot, or hot gases flying nearby, or anyway, those are the temperature of the surfaces. So what he wants is, what is the radiation heat transfer to the work floor when it's a 600 Kelvin? So he wants to find out how much, at the end of the day, how much Q will end up hitting that surface 1, Q dot 1. I mean, obviously, 1 will be on the receiving end when it comes to radiation, because both 2 and 3 are hotter than him. Okay? So this is what's required. We want to calculate this Q. Right? So the electric resistance equivalent to what's going on is basically this. There are 3 surfaces. 1, 2, and 3. And you would think, well, there are 4, but actually because those two sides of the two side walls are exactly the same, we could reduce the number of unknown rather than say we have 4 surfaces. We can call them 3. And though that side wall, whether it's to the right or to the left, it's basically the same surface. It's surface 2, right? Because of that geometry symmetry, it will be exactly receiving the same heat from both surfaces, right? So 2 and 2 is just one surface. So we are solving this problem to calculate that Q dot 1. And I know it will be coming this way because he's the coldest one of them, right? But, you know, it's okay to assume it's like this and assume this one is like this and assume this one is like this, solve for them, and we will not be surprised when that Q1 will end up being minus 500 watt. That's fine. We know it has to be coming, not leaving. All right? So we are trying to solve for this guy. But as you will realize that in order to solve it, you will actually have to solve for those 3 J's. So let's first look at this geometry. What's going on? So every surface, he has his black body radiation, and because they have their own epsilon, all of them has epsilon 0.5. All surfaces can be taken as gray and diffuse and having a emissivity of 0.5. So here is the resistance of 1. Here is the surface resistance of 2. Here is the surface resistance of 3. And because of this, every one of them has his own J that's different from his black body radiation. Alright? And between 1 and 2, there is space resistance between 1 and 2. 1 over area 1 F12. And between 2 and 3, 1 over area 2 F23. And again, this can also be written as the 1 over area 2 F23 can also be written as raise your voice. Excellent. Age is saying area 3 F3 what? 2. Reciprocal rule. So rather than area 2 F23, it's area 3 F32. Why would that be useful? Because sometimes you could get one of them easier than the other, just in the table, or you will see in a second. Right? But we will work the table to get those 3 space resistance. Right? And those surface resistance, we have them. So let's not lose what we are trying to do. What we are trying to do is let's get this Q dot. So let's forget about all the detail. At the end of the day, how are we going to get this Q dot 1? Does anyone have an equation for me that will give me this Q dot 1? Remember, Andrew, in the two body problem, he basically said, you want to get the Q, just basically say 1 minus 2, EB1 minus EB2 over the 3 resistance. Right? Because it was just 2 terminal and all the guys in the middle. And that's how he got his Q. But here, where are we? Here, he will not be able to say, where is the 2 terminals? You realize that this Q over here is not the same Q over here, right? But in this Q is basically those 2 guys together. So can anyone give me an equation for the Q that we are shooting for at the end of the problem? We will use it to calculate the Q. What is the equation that we will use at the end? Say that again. Yeah, that works. So you are saying, but it's not exactly like this. You are saying Q dot 1 is Q dot 12 plus Q dot 13. Yeah, that works. If you resolve for those 2 Q's, we can add them and then that will be Q dot 1. Or actually easier, I would say it's EB1 minus J1 over R1. And so now, actually I know R1 and I know EB1. It's just the J1 that I need. If I solve for that J1, I'm done. I can get my Q dot 1. Right? So we are getting the Q hitting surface 1 just from the difference between its black body radiation and its radiosity divided by its resistance. Now the trick is to get this. So what's the plan to get this? You have to solve those three guys together. You have to basically say that this J exists in an equation basically for Q12. Q dot 12 is just minus this over the resistance. And this J1 and J2 exist for the equation for Q dot 13. This minus this over the resistance. And this Q dot 3 is J2 minus J3 over R. And adding those Q's together will be equal to this Q, adding those will be equal to this, and that will set the three equations C unknown. This should remind you of your circuits course, right? Exactly. Kirchhoff law, for every node, there is a current equation, I1 equal I2 plus I3, and for every resistance, there is basically the voltage equation, delta V over R equal the current. That's what we are going to do. All right? So, again, rewriting the problem, what's given is the epsilons, all right, and required is the Q1. This is what we are trying to solve for. All right? There are space resistance and there are surface resistance that we try to solve. The black body radiation, we got it. It's AB 3 sigma T3 sigma T2 sigma T1 all to power 4. You work those numbers and you have those values. Okay, so you have all the E black radiation. And then you come up with the resistance, surface resistance, R3, R2, R1. Simply 1 minus epsilon over epsilon area, 1 minus epsilon over area epsilon, 1 minus epsilon. You get all the resistance. Right? Then the space resistance, so that we can finish the circuit. So to get that space resistance, we have to hit the table for example, let's go 1 to 3. What are those? Those are two parallel plates, infinitely long. Which table is that? Can anyone help me? Where did I get this F13? Which figure? Can anyone help? So those are two plates 3 meters away from each other. And it's kind of 2D, it's not 3D, so we don't have to use this long equation. We can use the shorter equation. Can anyone help? But I would use this easily. Because that chart is, I don't like the chart that much compared to the equation. Right. So yes, you can use this one, but I think this one is better. Right. Especially that this one is not infinitely long. This is kind of 3D, and this is 2D. Right? So table 13 would work for us. So table 13.2 will work. And so you get F13 equal 0.42, and because of the symmetry, F13 is the same as F22. Right? So right now you are wondering, well, why do we need F22? Because all I see over here is F13, F23, F12. Those are the guys that I would like to get. Right? But you will see why in a second. Or actually, maybe we don't really need F22. So we just need F13. So now, so we are done with F13. Let's try to get, say, F12. So how am I going to get my F12? So he's basically saying, well, F12 plus F13 plus F11 should be equal to 1. Summation rule, right? everything leaving 1, going to 2, and going to 3, and going to its own 1, that's basically should be 1. And f11 is 0, therefore f12 and f13 equal to 1. So f12 is 1 minus f13. Note that it's very hard to find f12. Why it's very hard to find it in the table? Because that's a flat surface radiating to two perpendicular surfaces next to it. You probably will not find it. You'll probably find only f1 to a normal surface next to it. And then you maybe have to multiply by 2 if you have the other two. Right? So he's using the summation rule to come up with f12 basically as 1 minus f13. Okay, so it's 0.52 and he's done with f12. So f12, what its relation to f23? f12 and f23 should be the same because of symmetry. I mean 2 representing to 1, what 3 represent to 2, exactly. Right? So it's basically because of the symmetry. So this is just the symmetry. That f12 is exactly f32. Alright? Except that here he didn't ask for f32, it's f23. The way we wrote it is f23, but that's okay. You can switch this to a3 is f32, or basically you can use it from the equation and you come up with f23 out of it. Right? So it turned out that f23 is 0.21. Right? So depending on the geometry, you will manage to get all the space resistance. Right? So now we have the black body radiation, we have the surface resistance, we have the geometry resistance. All those guys are given. What we don't have and we are trying to calculate is a Q. Specifically that Q dot 1. And here is the analogy to basically circuits. Right? So if you want to calculate the current coming to the circuit, you write the equation for, this is the equation for every basically every node. In this node, he's basically saying that the current coming here, or the flow rate coming here, or the heat transfer coming here, is basically going to be split. Right? So let's start with this point. So that Q, which is EB1 minus J1 over R1, is going to be equal to this plus this. J1 minus J2 over whatever resistance they have, plus J1 minus J3 over the resistance between them. This is one equation in how many unknown? How many? 3, J1, J2, and J3. But you do it again at this point and at that point, and you will get a system of 3 equations in 3 unknown. J1, J2, and J3. Alright? You solve them together and you'll get J1 and J2 and J3. Let's actually see the second equation. So this is for this point, for that node, and he's saying that the flux coming here, the heat transfer here, AB minus J2, AB2 minus J2, and remember AB1 and AB2 are we calculated them because we know the temperature, we know them. So here AB2 minus J2 over R2 is, and notice that this time he will actually say J2 minus J1 plus J2 minus J3, and then you shouldn't be confused. How come one time he calculated this way and the other time he calculating it that way? That's okay, because all he's trying to say is that the Q coming here will be split into those two directions. Right? This can actually be negative. I mean, this number could end up being negative. That's okay. Q itself, as we know, actually Q1 will end up being negative. So that's okay, as long as you are assuming the right, I mean, you're assuming it's in this direction and you're writing the equation correct, you are fine. So let's do it again for the last point to see how we did this. So over here, he's basically saying the flux coming here, that's E black 3 minus G3, E black 3 minus G3 over R3. See this? Is equal to this plus this. G3 minus G1 plus G3 minus G2. G3 minus G1 plus G3 minus G2. Each one of them is divided by the resistance in that place. So again, 3 equations and 3 unknown. Alright? So you can solve them by elimination, right? From the first equation you get G as function of 2 and 3, you plug it in the second equation, and now you have G1 and J2, you put it in the third equation, and now you have equation in only J1, you solve for J1. Or you just hand the matrix, you know, if this was actually a project or a homework problem, you hand the matrix to MATLAB and tell him here, 3 equation and 3 unknown. Get me the solution. And you will get your solution, and here is the J's. J1, J2, and J3. Right? So can this be in the final exam?
No.
The equation can be in the final exam. So I could tell you, write the equation that will give me the solution. Don't solve for it. All right? I just did this for a homework in experimental fluid this week. Because it was partial differential equation. So I told them, well, write the equation, don't solve them, but just give me the equation that,
So
all right?
If you were to do something like that, you'd have a solution.
So you finish here.
Those equations there.
That's the end. Well, together with this is the J's. You need to write this equation for me. Because so I have the J. Where is my Q? The problem asks for the Q. So the Q is, now once you get your J1, now the Q is EB1 minus J1 over the resistance. EB1 minus J1 over the resistance. Well, not surprisingly, it's minus 159 kilowatt per meter square. Why the minus? Because, I mean, look at that. 1700, 1400, and you are 1600. What do you expect your Q dot 1 would be? It will always be N. You will get radiation in that furnace. At the floor, you will receive radiation, not send radiation out. Okay? Question about this? So what's going on is that there is surface resistance that we have to calculate. Okay, if you are not black body, and you will not be a black body for most problem. And then there is geometry resistance, and we will basically call it, say, area 1 F13 or area 3 F31, and there is table for those F. And you write the equation that describes the heat transfer going through. It's basically difference between the J's over the resistance. Okay, and if you are lucky and there is a standard geometry, you just hit the table for that formula. All right. So let's look at one of those standard formula too that we could use. This actually was in the final exam last year. All right. So first of all, this is the flow or the heat transfer between two large parallel plates. All right. This was in the table that we visited earlier. It's this equation here. Right. Two parallel plates, infinitely long. They don't see anything else in the world except themselves. So that would be the Q between them. All right? That's equation 1338. So now what he's saying is, what if you have a shield between them? You are trying to reduce the heat transfer by radiation. So you put a metallic foil, shield between them. That's perfect for radiation, right? Because they have very large, very shiny surface. His epsilon will be very small, right? His epsilon will be very small. So that works. So then we expect the Q with one shield to be much smaller than the Q with no shield. This is a Q with no shield, and this is a Q with one shield. So what does this guy did when we inserted him like this? He added this, right? He added two surface resistance, his own epsilon. All right? And rather than having just one of those guys, you have two now. You have two geometry between those, right? Although this, we know that this will end up being 1. F32 is 1, right? They only see each other, so this is really 1 and 1. But anyway, so here is the formula. All right? So you don't have to all those formulas, you don't have to prove them to me. You just use them as they are. Here is the formula for heat transfer with a shield. I mean, you know why it's like this, right? But you go ahead and use it. So now what if we have a lot of shields, not just one? I mean, we will really want to kill the radiation. So let's add more and more surfaces between them. So if you keep adding more and more surfaces in shield, okay, if you add n shield, you will basically, every time you add one of them, you will basically add one of those brackets, okay, and you'll add a lot of them. So here is the formula that you would use for n shields, okay. So to start with, this is the formula if they have different epsilon, but if all of them has the same epsilon, that makes the problem much easier. This would be the formula. It's as if basically you are taking the Q with no shields, okay, it's this guy, Q with no shield, and you are dividing it by 1 plus 1. So if you have 10 shield, you are reducing that Q by 11. You are dividing it over 11. That's only how much you will be passing by. Right? And where this come from? Because of the extra resistance they are inserting every time you are adding one of those shields. The surface resistance for radiation for both of them, both sides. Okay? So let's look at this problem here. It's not a quiz. But basically said two very large barrel plates are maintained at 600 and 400. The surfaces are opaque, diffuse, and gray. He gave you epsilon 1, epsilon 2. Please determine the net rate of radiation heat transfer between the two plates. So what should I do? Can anyone help me? What is the formula? So Bob is saying there is in the table, there is the table between heat transfer between two concentric cylinder, two concentric spheres, two infinitely long barrel plates. Just use the formula. Exactly. That's what you do. So what is that formula? Just read it for me. A sigma
times T1 to the 4th minus T2 to the 4th over 1 over epsilon 1 plus 1 over epsilon 2 minus 1.
1 over epsilon 1 plus
1 over epsilon 2
plus 1 over epsilon 2
minus 1.
minus 1. Right? So I don't see the area. I don't see the area. But look at that. He asked it for watt per meter square. So basically he's saying just give me Q by area. Q dot 1, 2 by the area. Right? That is all he's asking about. So we know the sigma. 5.67, 10 to minus 8. Right? T1 to power 4, that's 600 Kelvin. Make sure it's in Kelvin. Don't make it in degree. I will probably put it in degree C because I'm mean. Right? I'm waiting for you to make the trick, to fall for it. 400 to power 4 divided by, and here is the 2 epsilon, right? We have 1 over 0.5 plus 1 over 0.9 minus 1. Right? That's it. And how much we get? 2793 watt per meter square. Okay. So that was in the exam, but then he said, what if we have basically a shield or 10 shields with that particular epsilon? What do you do? Well, you go back to the book for Basically, Q is one shield. If I add one shield, then look what he did. For one shield, what's the difference between the formula that we just used and this? It's this bracket, right? It's those two guys that you just added. Right? So you just use this formula for one shield. And if you add many shields, we'll add as many as you want. Those are all the new shield that is adding them. Questions? So, as always, we kill the heat transfer by adding resistance in the pass, adding resistance in series. That's what killed the heat transfer. And if you're going to increase it, you try to reduce the resistance between them.
So just to be clear, to use that one little shortcut where all the emissivities are, the surfaces are equal.
This is only if all the epsilon 1 and 2 and 3, the surface 1 and surface 2 and the shield, they all have one value, and that's epsilon. Then it falls down to this. If they are different, you cannot use this formula. You have to use this. Right? Very good. So, now this is I think the last one. I think we'll cover it. So this would be the losses that you would encounter when you are trying to measure the temperature. Okay, and there are two mechanisms acting in you. There is convection and there is radiation. Right? So this T thermometer is supposed to be, if you're doing a good job, should be TF. Right? If you're doing a good job, it should be TF. It's not going to be TF. Why? Because that thermometer that you are measuring its temperature is also radiating to the wall and convecting with the air. And he will reach a steady state where anything that he gains also will be lost, so that his temperature doesn't increase, doesn't decrease. Instead, stand at one temperature. So at steady state, that's what will happen. Q convection to the sensor is Q radiation from the sensor. This is assuming T wall is actually the lowest one and TF is the highest one. The problem would be reversed if the wall is really hot and the air is really cold. Then you will be getting radiation from the wall, losing radiation to the air. Sorry, losing convection to the air. But at the end of the day, the two mechanisms, basically one of them, the highest will take from you and the lowest will get from you. Right? So here is the convection, as always, AH delta T, and here is the radiation. And look at this radiation. This epsilon sigma T minus T, that's the, let's look at our table. Which formula was that? Which formula was that? The first one, right? This is basically a surface that's very small compared to his surrounding. So that pulp of the thermometer is very tiny compared to the duct that this, or the room, or the furnace, or the place where it's inserted in. So that's why the equation is area sigma epsilon T minus T. Your area times your epsilon. Right? So I didn't really get this problem in an exam for a long time. So maybe it's time this year. Right? So let's try to understand it very carefully, what will happen then. So again, area, which area? Area of this pulp. Epsilon, what epsilon? Not the wall. Your epsilon, the pulp epsilon. Right? Sigma T thermometer to power 4 minus T wall to power 4. So at steady state, this should be equal to this. So mark this equation in your textbook. This is what really matters. It's the formula for calculating the TF from T thermometer, because this is what you are going to measure. This is what the reading would be, but this is what you're really trying to find out. So the problem would be, say, a thermometer reading 80 degrees Fahrenheit, while he's sitting in a duct, the duct is sitting at this wall temperature, what would be the actual air temperature? And so the actual air temperature would come from this equation. So this equation is correcting T thermometer by radiation and convection. Can you read it? Which equation is this? Can you tell me the page number? 762, page 762.
Number 1346.
1346. That's the equation. So this equation correct the thermometer by radiation and the convection to get you the true TF. All right? Question? All right. So far, and actually during this course, I mean in the exam also, we always look to the air as if it is transparent for radiation. We basically, when we said the radiation, we said basically radiation just come from this surface to that surface. But what about the air between them? Doesn't the air absorb anything? And so over here is basically saying that, well, some gases basically would really participate in the radiation process. Right? They may participate in the radiation process by absorbing. Right?